All right. Hello, everybody. Can everyone hear me well? Please let me know if you cannot hear me. Okay, awesome. So welcome, everyone, to the first lecture series or lecture of this semester. Really exciting. Thank you all so much for being here. If you don't know me, my name is Alina. I'm the outreach coordinator for the Cornell Astronomical Society. And today we are welcoming Professor Dongwoo Chung of the Department of Astronomy here at Cornell. Their research largely focuses on developing new ways to map and understand how galaxies formed and clustered in the early universe. So today they'll be giving a talk about early radio astronomy and how it relates to a new astronomical survey method being developed. So please join me in welcoming Professor Chung, and I hope you all enjoy.
Thank you, Lena, for the introduction. Thanks, everyone, for showing up. Some of you have been in some of my classes. Some of you work with me in research, and so you know how quickly I might go through some of this stuff. So apologies in advance. But I do want to talk about different ways, both old and new, in which we have gotten these almost chance encounters with some of the most important kinds of observations that we make of the universe to understand what's going on. Now, these surveys in radio wavelengths, millimeter wavelengths, they use very different kinds of telescopes from ERV, but I do have some history with ERV. I actually visited Cornell back in 2022 whilst I was still based out of the University of Toronto, where I was a postdoctoral researcher, because one of the grad students that I work with at Toronto, here is Dang Pham. Dang actually came out of Cornell as an undergrad, and he was in CAS. And so when we came back here for a collaboration meeting, we actually attended one of these Friday open houses, and I'm pretty sure the dome was not working on this day, and we just went out on the back and looked through the other telescopes that were not ERV for that day. But it was still memorable enough that when I came back, I was like, oh wow, I get to just commute past Fortes every single day, so that's great. And more recently, I had the privilege of attending the event around the lunar eclipse that you all organized, which was great. It was shockingly well organized for the amount of people that you got. And I did have to commandeer some of your telescopes to get photos for the class that I was teaching at the time. But today I'm not here to talk about that. I'm here to talk about some of the research that I'm doing. In particular, again, looking at the universe in ways that you might not necessarily think about when we're thinking about looking at astronomy through these conventional telescopes at these conventional objects. And it's all in the service of answering this question of how did we get here? And if you want to expand that out a little bit, we're talking about how did we get here and now from the Big Bang, this intense, hot, dense state that the universe starts out in, this state that has been often called like a primordial fireball. How do we get from that state to galaxies that we see around us, galaxies that we see from billions of years ago, to galaxies like our own Milky Way, with stars, planets, life. In at least one case, how do we get from the Big Bang to humans? And ultimately, as Alina said, my research is kind of focusing in on how do we get from the Big Bang to galaxies in the first place, and I kind of leave the stars and planets bit to a lot of other folks. But that is the thrust of the research, and I want to talk a little bit about how we've kind of gotten to this picture in the first place through some very unusual historical instances before I really talk about my research. Now, in the 90s, actually, this is I've gone from the picture to a little bit too small a picture. Let's zoom out a little bit. So in the 90s, when the Hubble Space Telescope first launched, one of the observations they made was not of the Orion Nebula or a planet, but rather this very small piece of very blank sky where from the ground, you don't see any stars, you don't see any bright object. But in the 90s, they said, look, we're going to look at this patch of what we think is blank sky for many, many orbits, and we're going to see what comes out the other side. And what they saw, indeed, in this seemingly insignificant blank sky with maybe a few stars scattered about. What they saw was what we now know as the Hubble Deep Field, right? This vast array of galaxies spanning the entire history of the cosmos from a billion years to 14 billion years ago. And this is how we learned, in a great sense, that everywhere you look, there are just galaxies waiting to be discovered from long, long time ago. But this was not really looking for any specific one of these galaxies, right? This is basically saying, wherever you point, you're going to find something interesting. And that principle of kind of serendipitous discovery, one of the most interesting examples to me is of Karl Jansky. Now, Karl Jansky was not an astronomer by training. He was a physicist. He was a radio engineer. He went to work for Bell Labs, which was the monopoly operating the telephone lines back then. And he went to work in New Jersey, and he was looking at transmission of radio waves with an eye to use this for wireless transmission of communications, of phone calls, for example. And so to that end, he actually ended up discovering the entire field of radio astronomy instead. Now, how did he do this? He built what we now call a merry-go-round. He basically built this radio antenna, and in particular, this is a directed antenna, so you receive radio waves from a specific direction. And then, the important part, why it's called the merry-go-round, you can see very, very faintly here, this turntable here, with the wheels on the turntable to let it orient in any direction you want. So this is a steerable radio antenna, and effectively he had built the world's first radio telescope. The question, though, is what did he see? Well, he saw a lot of noise, really. He saw thunderstorms. Whenever there was a thunderstorm nearby, he would see something on this readout here. Whenever there were thunderstorms further away, he could tell that there were thunderstorms, not because he could see them, but because there was this static that was similar to what you would see in the local thunderstorms that he was able to confirm visually. They were steadier, they're much fainter, so there is kind of a random background of these thunderstorms from very far away that are still showing up in his merry-go-round. And then he saw a third signal, which he was not looking for, which he could not, correlate with anything that he saw with his eyes. But it was this what he described as a very steady hiss-type static, the origin of which is not yet known. And basically he figured out by 1933, after some time, he figured out that this static, wherever it was coming from, it was repeating with a periodicity of 1 day. To be exact, 23 hours and 56 minutes. So not quite your calendar day, but your sidereal day. So it's moving specifically with the celestial sphere. And it actually turned out to come specifically from somewhere in the constellation of Sagittarius. Now, Sagittarius, as you can see, not only encompasses the teapot that you're familiar with, the actual constellation, but it also encompasses the center of our galaxy. And so what Karl Jansky was seeing with this very steady hiss-type static was as the Earth was rotating, as we were going through each sidereal day, the galactic center was crossing the field of view of his merry-go-round. And so, indeed, he talked to astronomers and he was able to confirm that there were these radio waves coming from the center of the galaxy and the center of the Milky Way turned out to be the source of this mysterious static. And this was so notable that amidst the chaos of the prelude to World War II, amidst the chaos surrounding the aftermath of the Great Depression, this made the front page of the New York Times in 1933. And as well it should, because this is an astonishing insight, right? We can learn things about our galaxy not just by looking at the stars and looking for patterns in the stars, but looking for patterns in the electromagnetic waves that we cannot even see with our own eyes. The next anecdote I want to talk about happens actually again in New Jersey, again through Bell Labs, but 3 decades later in the 60s. So at this point, Bell Labs says, we are, in the middle of the Cold War, we're interested in satellites. Let's say for now that they're communication satellites and they're harmless civilian communication satellites, but we want to look at satellites, we want to look at sending radio signals to satellites, receiving signals from radio satellites, and we want to build this giant steerable directional radio antenna, which, like Jansky's merry-go-round, but much better directed, can act as a radio telescope. So in particular, there were two Bell Labs employees, Arno Penzias and Robert Wilson, and they basically made plans to look at the Milky Way with this antenna, just as Jansky did accidentally with his merry-go-round. And in particular, their radio receiver operated at this wavelength of 7 centimeters. For reference, of course, red light is around 400 nanometers, so this is very long wavelength indeed. And they wanted to survey the Milky Way. They wanted to potentially look at hydrogen gas in the Milky Way eventually, but they had a snag. Even before they could move ahead with their plans, when they were starting to test the receiver out, they started to see excess noise in their instrument, and they couldn't account for where that noise was coming from. So this is one of the careful plots that they made, just as Jansky was sitting there, with his roll of paper, looking at the static as it was being read out. Penzias and Wilson, were making pretty serious notes about, the kind of voltage readings they saw, the kind of power levels they saw, what they were looking at. They had a calibration device to calibrate how much power they were seeing, how that related to the voltage they were seeing from the receiver, and so on. But the point was, when they were looking at this particular source called Cassiopeia A and comparing to a cold load, a type of calibrator source, they were seeing an excess temperature of several Kelvin that they couldn't really account for from it, based on any of their sources. They saw this in mid-1964, but just like Jansky in 1933, it took some time for them to actually figure out what was going on. Again, both Jansky and Penzias and Wilson, these are careful scientists. They were methodical in trying to come up with different explanations, different tests to test their explanations for what that excess few Kelvin could be. Now, I want to pause for a moment and imagine this is already banquet seating. So imagine you're in the cafeteria of Bell Labs in New Jersey, and you're listening to Arno and Bob talking about this, temperature on the sky that they're seeing, like this 3-4 Kelvin excess. Now, some of you, possibly many of you, already know where this story is going. But if you don't, without the benefit of foresight, what possible things would you suggest that they check for? Instead, this 3-4 Kelvin temperature, what possible sources of that excess temperature, what possible sources of radio noise, should you check for? What tests might they do to check into their sources? Does anybody have any suggestions for 1964 Penzias and Wilson? Take the machine to the lab? Look at a machine that's generating noise and basically point it into like something that generates the noise and try to compare what they see. Okay, anything else? Okay, something that they didn't detect that's kind of heating the antenna somehow. Okay, any other, what do you think they would, how do you think they would test for that? What should they be looking for? Where should they be looking for? How? Okay, any ideas? Okay, check for nearby radio stations, good idea. And? Different times of day, different locations on the sky. Great, these are all great things to think about, and indeed, Penzias and Wilson did go through some of these tests. Some of the other tests that they did, is the atmosphere more opaque than we thought? Because the atmosphere itself, is not negligible when we think about temperatures in the range of Kelvin. Even at these long wavelengths, we of course realize that in ultraviolet light, the atmosphere is very opaque. In radio, it's not really that opaque, but it still is about 1% opaque. So as a result, you might see a few Kelvin excess if you've just slightly misestimated your opacity. But they were able to point the antenna at different angles on the sky. And of course, if you've seen the sun over the course of the day, the opacity of the atmosphere apparent to you depends on the elevation angle that you're looking at. And indeed, when they oriented their antenna at different angles to look through more air, less air, their results showed that basically the sky was as hot or as opaque as they thought it was supposed to be. Another thing that you may have heard about if you're familiar with the story, pigeons. Are pigeons causing the antenna to act noisier? So this might be one of the excess sources of heat, right? If you have pigeons living in the antenna, and if they are depositing pigeon droppings in the antenna, that is going to cause your antenna to act noisier. So they did their due diligence, they cleaned the droppings out and, quote, disposed of the pigeons, unquote, and I refuse to learn what that means. And apparently that only made a minor improvement, so I hope they thought that was worth it. Someone mentioned radio stations, but I bet you didn't think about nuclear tests. In 1962, there was a nuclear test called Starfish Prime, which was a megaton-level warhead that was detonated 400 kilometers above sea level, basically the same altitude as the International Space Station. And what that meant was that there was this huge outflux of radiation, charged particles basically going across the sky. There were aurora visible as a result of Starfish Prime. If you looked at it from Honolulu, it looked like the sun had just come up at 11 p.m. And basically these charged particles, maybe they're still circulating through the atmosphere after years. Are they injecting additional noise? So they actually altered their apparatus to shield it better against interference from charged particles. They still saw this excess temperature. And indeed, is it some kind of ground signal? Is it a radio station? Holmdel, New Jersey is within driving distance of New York City. So is this coming from New York City? Is it some other discrete source in the galaxy that they didn't account for? In which case you should see different things when you look at different locations and different times. And they basically spend a whole year. So, a whole orbit around the sun, looking at different parts of the sky at different times, and they saw this excess very, very consistently. And so at this point they say, okay, look, there is, I don't know how, but there is, everywhere we look, there is about, 3 Kelvin, 4 Kelvin more brightness around on the sky than we think there should be. So they finally, in 1965, move ahead to publish this. And while they're doing this, while they're preparing this publication in the Astrophysical Journal, they managed to get on the phone with a professor at Princeton, Bob Dickey. And Bob Dickey was one of these people, one of these cosmologists that was actually trying to detect an excess temperature of roughly 3 Kelvin that should be everywhere in the sky. He was building an instrument on the Princeton campus to try and detect this kind of excess. And so he got off the phone and then he told his postdoc, we've been scooped. Thankfully, this did not sour relations between them or anything like that. They coordinated, the two teams basically coordinated a set of publications. Penzias and Wilson published their detection, and Dickey, along with Jim Peebles and Peter Roll and Dave Wilkinson, they basically coordinated a companion paper where they provided a possible explanation, what we now know to be the actual explanation for that excess noise temperature. And that explanation is cosmic black body radiation. There is a 3 Kelvin black body that permeates the entire universe around us. So, if you're familiar with the story, you know the ending, which is that Penzias and Wilson won the Nobel Prize. And for his trouble, Jim Peebles, Bob Dickey's poor postdoc, he did win the Nobel in 2019. He had a long, prosperous career in physical cosmology. And this, like Jansky's discovery, made the front page of New York Times because this was big. This was what we now consider to be the smoking gun, so to speak, for the modern Big Bang model of cosmology. And the reason is this, right? There were two competing models of cosmology at the time. There was this idea that the universe is in a steady state we knew the universe was expanding, but steady-state theorists basically posited that the universe is expanding because there is always matter being created and basically expanding out into this, continuous steady state of the universe. Other folks drew the conclusion that if the universe is expanding, you can trace that all the way back, and at some very distant point in the past, all that matter must have been concentrated at some singular point in this hot, dense state. George Lemaitre, who was one of the theorists that actually presaged Edwin Hubble's result for the expansion of the universe, he called this idea the primeval atom. But Big Bang seems to have caught on a lot better, which is ironic because Big Bang was a moniker coined by Fred Hoyle, who was one of the Big Bang model's greatest detractors right up to the end of his life. But in any case, if the universe was that hot and that dense at some very distant point in time, and that was basically the state of the entire universe, we should be seeing the afterglow of that fireball. And so this is what George Gamow predicted before Bob Dickey. This is why Bob Dickey wanted to build a radiometer to measure some excess temperature. And this is what Penzias and Wilson found purely by chance, just like Karl Jansky found the center of the galaxy, essentially purely by chance as well. So this is what the Big Bang model effectively says, right? The universe at some distant point in the past is completely hot, dense soup of ionized particles, photons coupled together in this fluid that's basically impossible to distinguish anything from anything else. And, basically around 400,000 years after the Big Bang is when we see the photons that make up that cosmic blackbody radiation start to actually decouple from the matter part of the soup. At this point, the temperature of the universe has cooled down to 3,000 Kelvin from the millions of Kelvin that we think it probably was before then. The sun's surface temperature, for reference, is about 6,000 Kelvin. The sun's surface and this radiation will be called the cosmic microwave background. These both behave like black bodies, which means just that they are bodies at some temperature at thermal equilibrium. Because the apparent color of a black body changes with temperature, the sun is yellowish white. A 3,000 Kelvin black body, on the other hand, looks a little bit warmer than that. So as time passes, you will see not only the overall level of that black body change, but you'll also see, these little imperfections in what is otherwise this very homogeneous soup. These imperfections, which we only see an instant of because we see these photons stream away from what the matter looked like 400,000 years after the Big Bang. Underneath all that, we will see that matter over time coalesce into the kinds of structures that we're familiar with. These variations in the afterglow of the Big Bang, these variations in the CMB temperature, on top of the 2.7 Kelvin average, these variations tend to be on the order of 40 parts per million across the sky. That's kind of a general figure. Of course, individual variations can be stronger. The color scale here spans, up to around 200 parts per million. But these are very, very small variations, which is interesting, right? Because you have these very small variations 400,000 years after the Big Bang. But, of course, the variations that we experience now around us are much larger than that. Now, how does this happen? Well, we have to wait a while. So 400,000 years after the Big Bang, we're at 3,000 Kelvin. The universe is still a huge homogeneous soup of stuff. About 1 million years after the Big Bang, we're now at about half the temperature, and it's still kind of a soup. 2 million years later, 1,000 Kelvins, the black body of the CMB looks redder and redder and redder, going into longer and longer wavelengths. In the present day, of course, we see this at radio wavelengths, like Penzias and Wilson did, predominantly at those radio millimeter wavelengths. But we don't have all the time for that. We're just going to fast forward a lot because, we're seeing the universe grow redder and redder, but also darker and darker. And you might ask, well, who turned out the lights? Where is all the light going? The universe was in this hot, dense state. Yes, but that's kind of the entire universe doing that everywhere all at once, like we were in the middle of the sun. And now we're kind of watching that stellar interior like environment kind of expand and cool. And there are really no discrete objects at this point in time. So at the start, right, you have the universe full of light, but light that is basically completely trapped in this plasma of ionized particles. About 400,000 years afterwards, at this time we call recombination, that's when the CMB is emitted. The entire universe basically becomes transparent because now that plasma, all those charged particles, have cooled down enough that they neutralize into atoms, and they don't have as much opacity as electrons do. So they have one last Thomson scattering event against the electrons, and they emit, and the light goes away all at once. And now what's happened? All the atoms have recombined. The universe now is this bath of neutral hydrogen. Neutral hydrogen by itself doesn't really do anything that interesting if it's just kind of spread across everywhere in the universe. And the photons are just kind of streaming through it. And there's really nothing there to kind of emit any kind of discernible light until we start forming objects. And that takes time because gravity is not a very strong force. It takes, again, 400,000 years from the Big Bang to the emission of the CMB, that time of recombination. And what we call the cosmic dark ages, this time when there's just neutral hydrogen in this, homogeneous, boring, complete porridge, the duration of the cosmic dark ages is over 100 million years. So it takes a while for light to actually start coming out of the universe again. But as you wait and wait and wait, what do you see happen? You see these structures form out of those very small inhomogeneities, those parts per million inhomogeneities that you saw reflected in the inhomogeneities of the Big Bang, of the CMB. Those inhomogeneities in the matter distribution have been slowly, through gravity, slowly coalescing, collapsing, until you start encountering instabilities. And those instabilities grow and grow and grow until you start seeing what you might start to recognize as shapes. And those shapes eventually start turning into objects. Now that requires you to cross a certain threshold of instability. And that instability is going to be crossed more easily for smaller objects compared to larger objects. So it takes even longer to see modern galaxies, what becomes the seeds of modern galaxies, compared to what basically becomes the structures underneath the first stars. So again, 100 million years, nothing forms. But around 400 million years or so is when we think there are matter waves across the universe that become large enough to form these instabilities that then form into the first stars, that those stars then finally light up the universe again. Again, some 400,000 years after the Big Bang. This, of course, what I'm showing you here is a complete, complete fabrication from whole cloth. This is not tracing any particular part of the universe in any way. This is basically saying, this is an illustrative way to show it. But something like this, statistically speaking, happened around 400,000 years after the Big Bang. And so as this proceeds, you form more and more stars, and those stars, importantly, emit ultraviolet radiation that, of course, our atmosphere shields us from, but ultraviolet radiation that nonetheless then dissociates all the neutral hydrogen, breaks up those nuclei and electrons back up into this ionized state. And in particular, as that happens, energy gets transferred into that interstellar medium, the medium between stars, and that in turn provides more and more impetus for these instabilities to grow and grow into more and more stars. There is a bit of a chain reaction going on until you end up with all these galaxies formed from those stars, all these structures formed from those galaxies in many or over dense regions across the entire universe. So that, briefly speaking, is the history of the entire universe as we know it today. You have the Big Bang, you have this period of recombination when the universe goes from fully ionized to neutral. You have hundreds of millions of years of what we call the Dark Ages until gravity has taken its toll, causes these instabilities that emerge as the first stars. Those first stars form into the first protogalaxies. Those protogalaxies then merge and evolve into the kinds of galaxies we recognize today. So this first billion years after the Big Bang is a pretty pivotal epoch in our cosmic history. And of course, in the subsequent 13 billion years, there's a lot of evolution of these galaxies to the point where we can recognize them as galaxies. Now again, to look at all these galaxies, we use these light buckets like HST, like the Hubble Space Telescope, but we also use all kinds of different telescopes to look at things in different ways. Why do we do this? One, as I hinted, as time goes on, light does not stay constant. As space expands, for example, the cosmic microwave background itself cools down, the light waves stretch and stretch to longer and longer wavelengths, and individual objects, the light from individual objects that are very far away, will also stretch with the expansion of space. And as a result, what you have is this effect of cosmological redshift. As distant objects that are emitting ultraviolet light because they are forming stars, that light may look like it's emitting in the infrared to us because of this effect of cosmological redshift. So if we want to learn about ultraviolet radiation that is coming from galaxies from the first billion years, we actually need to look in the infrared. So in addition to Hubble, which looks at the visible wavelengths, we have JWST, for example, looking in the near infrared. But there are also other wavelengths that are worth thinking about, and you encounter one of the examples every time you fly out of Ithaca Airport, or Syracuse, and in particular, you encounter it here in this full-body scanner, because what the full-body scanner is doing is it's surveying you. It is surveying you in somewhere between the infrared radiation and microwaves, millimeter wave light a lot of the time. And in particular, why is it doing that? It's doing that because millimeter wave light is transparent to things that optical light is not. And so, in principle, a security screening can detect things that you are concealing to human eyes, but you cannot conceal to these scanners and other wavelengths. Just in the same way, by scanning the universe in different wavelengths, in addition to looking at redshift and emission, you're just looking at different things happening in the sky and objects all across the universe. And an extreme example of this is sometimes very specific wavelengths can tell you about very specific things that are happening. And you see this in spectroscopy. So when you disperse light into all the wavelengths that we see put together, you can see, for example, that the spectrum of the sun is actually explained by a composite of different spectra from different elements or different molecules with potentially different pressures, for example. And so can the spectra of individual nebulae. This is, for example, how we know that nebulae look different from our sun, because in particular, nebulae tend to have emission lines that are very prominent, as opposed to this continuous spectrum that we expect from the sun. And in particular, you may know that the element of helium is named as such because it was first discovered not anywhere in a terrestrial observatory, but for the first time by looking at a stellar spectrum of the outer solar atmosphere during an eclipse. In particular, these two lines here are the sodium lines, but if you do very fine spectroscopy, you can see a line that is not explained by the emission spectrum of sodium, and that line was correctly attributed to an element that had not been terrestrially discovered, that element being helium. So very specific wavelengths can be attributed to very specific kinds of chemicals. And of course, we want to look at this in all kinds of different wavelengths, and not just optical, as is the case with helium, but also with radio waves, millimeter waves. This, for example, is the Atacama Large millimeter wave array in the Atacama Desert in Chile, which is a very nice site for observing in millimeter wavelengths. And in particular, those two instruments that I was showing you, HST and ALMA, those can reveal different things about these deep fields of galaxies. This is no longer the Hubble Deep Field, this is the Hubble Ultra Deep Field. But you can see, for example, that HST is showing you all of the stars in the galaxies. This is a fuzzier picture, but if you look very carefully, you can see these bright dots that are coming out of the noise. And those dots are not coming from the stars necessarily. Those are coming from, in this case predominantly, the dust that is present in all of these galaxies. The dust that is being heated up and is forced to cool by emitting not in the ultraviolet light that they absorb, but by emitting in the infrared light that we observed, and which is then redshifted to millimeter wave light for us to observe with instruments like ALMA. So this is all well and good for studying objects in detail, individual objects. But when we think about reionization in particular, when we think about this phase of the universe where the first stars are forming and they're ionizing all this neutral hydrogen around the universe, these events like reionization are, cosmic phase transitions. It's happening everywhere all at once, right? There is no particular point in the universe where reionization, on average, is not happening or is happening exclusively. This is a cosmic scale event where stars are forming everywhere, forming these bubbles of ionized hydrogen in this medium of neutral hydrogen, and these bubbles of ionized gas are coming together and merging to give us what at the end of reionization is this mostly ionized transparent universe. The trouble with trying to apply this principle of serendipitous discovery with deep fields like the Hubble Deep Field or the Hubble Ultra Deep Field, the trouble with that is that we may end up with a view of these cosmic phase transitions, these cosmic processes that are woefully incomplete. So here, in white here, this little cutout here is the size of the angular size of the Hubble Deep Field. This scale bar here is about 1 degree wide, and if you look back to redshift 2, which is not even in the middle of reionization, it's a few billion years after reionization is concluded. If you look back at redshift 2, 1 degree on the sky corresponds to 90 million parsecs, where a parsec, of course, is the distance to our nearest, roughly the distance to our nearest star, Proxima Centauri. And you can see that this is a pitiful extent of the cosmos compared to all the kinds of filaments and voids and peaks that you see forming at this time in the matter distribution of the universe, right? So, if you are surveying just this little extent, you could easily be looking at a particularly bright or particularly dim part of the universe. You're not getting the full picture of how things are happening across the universe. So you may serendipitously end up missing just as much as you're discovering. So at this point, we're kind of coming up, towards the kind of stuff I'm doing. But to understand the kind of stuff I'm doing, we've had to kind of take this long journey where we've been talking about all kinds of different instruments, looking at these faint distant galaxies from the first several billion years of cosmic history and all kinds of different wavelengths, and surveys with, for example, the Hubble Space Telescope, the Hubble Deep Field. These have been successful in resolving these galaxies, comparing them to, galaxies in the present day. What I haven't mentioned as well is that conventional galaxy surveys, you may have heard of the Dark Energy Spectroscopic Instrument, you may have heard of the Sloan Digital Sky Survey. Those kinds of surveys have been very successful in mapping out our local universe and in particular mapping out the large-scale structure around our local universe in 3 dimensions. But they have not been able to do that for faint distant galaxies because they are faint. And alongside, these deep field surveys with Hubble, these, large galaxy surveys, you have, of course, surveys tracing the cosmic background radiation. Now, we don't just detect the excess temperature across the sky like Penzias-Wilson did. We can look at these anisotropies in temperature. We can look at the way the polarization varies, which reflects how the photons made their last scattering event out off of the electrons at the surface of last scattering of that plasma. And these surveys of this radiation have been really successful in looking at what the universe looked like just 400,000 years after the Big Bang. But of course, that is just a snapshot of the universe. That doesn't give you a full picture of what happened between then and now. And of course, I've given you a couple of things to think about in terms of the different motivations behind all the different modes of observation, one of which is that different wavelengths look at different phenomena, and very specific wavelengths can reveal very specific things about very specific chemicals being present out there. And I've talked to you about the redshifting of light. So even though this wavelength here is associated with a very specific chemical, a very specific element, as you go back further and further in time, as you look at objects further and further away, that same frequency looks to you, that same wavelength looks longer to you, that same frequency looks lower to you as you go further and further back in time. How do we use this to look at the distant universe? How do we use this to characterize what's going on, for example, during ionization? So in the millimeter wave, we have these specific wavelengths, these spectral lines, accessible to us for local galaxies, for example, like the Large Magellanic Cloud. Some examples that I particularly look into are carbon monoxide. So carbon monoxide has rotational energy states that are discrete, that are quantized, and transitions between those energy states manifest as emission of specific wavelengths. And so this is tracing carbon monoxide, which is one of the most abundant and most bright species of molecular gas that exists, other than molecular hydrogen, which is very abundant but also not very bright. So you can use this kind of CO spectral line to trace molecular gas, which in turn is the kind of gas that actually ends up forming into stars. You also have what we call C2. This is a ionization state notation, so this is really singly ionized carbon. C1 would be neutral hydrogen, C2 is singly ionized carbon. And this is tracing gas that is being actively ionized, metals that are being actively ionized. But regardless of the specific spectral line you choose, well, if you're looking out at some particular line of sight and you're looking for a specific galaxy, you might expect to see a line. You might expect to see this particular frequency reflecting the position along the line of sight of that galaxy. But again, the Hubble Deep Field tells us wherever you look, there are lots and lots of galaxies. So if you had a very coarse kind of very coarse kind of telescope, and you looked for this line emission, you would also see line emission coming from all these other galaxies that are also along this line of sight. And what you would see is fluctuations in the total emission in the spectral line, this single wavelength that has been redshifted as you look further and further back in time. And the fluctuations in this total intensity reflect the fluctuations in the abundance of galaxies that exist along this line of sight. And then you can drag that line of sight right across the entire sky, and you have suddenly a tomographic picture. You have a three-dimensional picture of where all of these lines, where all of these carbon monoxide lines, C2 lines, what have you, where all these lines are coming from across the sky, how that relates to the galaxies that are emitting those lines, and indeed you have a three-dimensional picture of what the universe looked like. And this is the kind of thing that we want to do to look at this cosmic process of reionization, to look at the way stars form, to look at the way galaxies come together, you need to be able to look at these different lines. Again, specific wavelengths reveal very specific chemicals, and in particular, if you're looking for the overall abundance of this neutral matter, you would look for a neutral hydrogen line intensity mapping experiment. But if you were looking for sources of the ionizing radiation that eventually turns this whole thing ionized, well, then you might look for carbon monoxide, because that's where there's molecular gas, you have stars forming, or you might look for C2, because that's just a indication of very energetic star-forming galaxies that are emerging at this time in cosmic history. So this is kind of like looking for variation in the CMB, right? Variation in the CMB tell you what the fluctuations in the matter field are like 400,000 years after the Big Bang. Variations in line intensity can tell you about variations in the abundance of star-forming gas, variations in the abundance of neutral gas, and so on. Those variations are going to be possibly even smaller than these several dozen parts per million variations in the cosmic microwave background temperature. And we really need very sensitive instruments to undertake these experiments. And we need to be very careful about processing the data that comes out of these very sensitive experiments as well. So this is what I work on. There are a few experiments that I work on. This is the experiment that I worked on during my PhD. At Stanford University. I continue to work on it now. This is what we call COMAP. This is operated out of the Owens Valley Radio Observatory in the Sierra Nevada in Central California. It's led out of Caltech. And its goal is to basically map the universe in 3 dimensions with this CO line. I should probably actually put Ella on there, because Ella has been working with me on understanding some of the data in relation to galaxies that exists in the volume that we are surveying, the volume of the cosmos that we are surveying. This is what the actual instrument looks like, close up. The telescope itself doesn't really do the detecting. What's inside of here does the detecting. Just like Penzance and Wilson had a cold load, we have a hot load that kind of comes in front of the telescope and gives us a reference for the power. If you take that weather shield off, this is what the actual detector looks like. This is a much more sophisticated receiver, much lower noise receiver than the kinds of receivers Jansky or Penzance and Wilson would have used, but it is nonetheless, at the base level of it, similar technologies. Of course, now these antennae are much more directed compared to those kinds of antennas, but nonetheless, very similar kinds of technologies at the base of it. What's cool about this is that to operate these low noise amplifiers, you need to actually cool this instrument down to around, around 4 Kelvin, and that allows you to achieve a pretty reasonable level of noise performance for these kinds of receivers. But overall, this is still a pretty big undertaking. To process all the data that's coming out of these low noise amplifiers, you need racks and racks of logic boards that basically process what's coming out of these amplifiers into the kinds of spectra that we want to see in order to build up this picture, this 3-dimensional picture of the gas permeating the cosmos. So that's COMAP. In particular, we've been operating several different kinds of COMAP in order to match our different levels of ambition for mapping out, a test area of the cosmos, a much wider area of the cosmos, and then stretching this out to larger areas, further back in time as well. Another experiment that I'm involved in is called TIME, which is very confusing when you try to look this up on the internet. This is the tomographic ionized carbon mapping experiment. This is looking for that C2 line that I mentioned briefly. This is actually led by Abby Kreitz, who's a professor in the physics department. And Abby's actually lecturing here next month. So if you want to hear a little bit more about the instrumentation side of things in terms of general cosmology and instrumentation, you should definitely come to that lecture next month. This is kind of a different kind of worms here. There are different kinds of detectors that we call bolometers. Instead of taking the spectrum out through logic boards, we actually have to make the spectra at the front end and basically disperse the light onto these bolometers, which exist in a little bit messier way than you might hope. In fact, This is a picture of a partially integrated time receiver in the high bay of Newman Laboratory in the Physical Sciences Complex, just down in Central Campus of Cornell here. And Selena, who's in the audience as the graduate professional representative, has been looking at this. Is it cold yet? It's colder. Yeah. So I mentioned COMAP has to cool down to 4K. These detectors, they have to cool down to about 300 millikelvin, 0.3 Kelvin, in order to achieve the kind of noise performance that we want. At the end of the day, this doesn't operate out of Cornell. This actually goes out to Arizona, where there is a radio telescope that this gets lifted onto, which is very terrifying. And in particular, this is what the cryostat looks like once it's in the cabin. It is a very cramped sort of deal. You can kind of see I don't really have space to put my laptop anywhere, so I just had to kind of improvise. But we can still keep an eye on the instrument. We have a camera in the cabin, so as long as that's securely mounted, there should be no problem. It's fine. I went up there afterwards and kind of fixed it back up with more duct tape. But, and it was an interesting experience, this particular run, because this was still during the height of, the COVID pandemic. A lot of us were working remote. A lot of us were kind of having to do these debug sessions over Zoom to make sure the receiver was working. But at the end of the day, we got it working. And in particular, we actually went back to how this all started, right? We look back at the start of radio astronomy. We looked at the galactic center. This is an optical image of the galactic center. You can see there's not really much going on here at this level of scale because the galactic center is mostly obscured by dust when you look at it in the optical wavelengths. But when you look at it with time, which is built to be a millimeter wave receiver, a millimeter wave spectrometer, you get this picture of this circumnuclear material, this hot circumnuclear gas, and these molecular clouds that are surrounding the nucleus and are full, in fact, of carbon monoxide. And in particular, you can kind of break this out into different frequency channels, and again, very specific frequencies. Here we have this specific frequency telling you where all of the molecular gas is around the galactic center. So we're actually very excited because, we've done a kind of line intensity mapping. Not the line intensity mapping we want to do out in the high redshift universe, but we've certainly shown that we can at least, operate a spectrometer, which is kind of the first, base condition for operating this kind of very sensitive experiment. If you have a keen eye, you might notice that the flux here is in units of Janskys per beam, because Karl Jansky kicked off the whole field of radio astronomy. We named the unit of flux that is commonly used in radio astronomy after Karl Jansky, and it is somewhat poetic to kind of, after all this, as we're building these really sensitive experiments, almost a century later, it's kind of poetic to be looking back at the galactic center that Karl Jansky looked at, measuring the flux in CO from the galactic center in units named after him. I'm going to end off soon, but before I end off, I do want to mention the big thing that's coming up for Cornell Astronomy, which is that we're getting our own telescope, sort of, not really, but we're getting our own telescope. This is the Church Tora Atacama Telescope project, which is building a 6-meter telescope near the summit of a mountain in the Atacama Desert. So Alma, which I showed you very briefly, that is an array of telescopes lower down in the desert. This is an even higher site, so you're looking through even less air. This is going to be a fantastic instrument. This is going to be a fantastic facility to do the kind of stuff we're trying to do with COMAT, the kind of thing we're trying to do with time, as well as other observations, for example, of all kinds of different cosmic backgrounds that exist at this millimeter wave range. So in fact, we're actually having a collaboration meeting next week, which I've been trying to help organize, and we'll have lively discussions because this is actually supposed to see first light next spring. So be excited. We should hear more about this CCAT project in the near future, and perhaps CAS will invite some astronomy faculty to talk about this project in the near future as it kind of comes online. And again, these look very exotic overall, and this is going to be a pretty big array of detectors scanning across the sky. TIME has around, like 1,000 different lines of sight. COMAP has only 19 lines of sight, but this is packing in 6,000 lines of sight looking across the sky. So very, very excited. So that's where I'll wrap up. And the point here is, by building these cutting-edge instruments, these spectrometers, and by being able to make sense through hard work of extremely faint signals that we detect with these sophisticated instruments, the research that we're doing here is really going to connect the dots of cosmic history from the Big Bang through reionization, through the emergence of the first stars and galaxies, all the way to the galaxies that we see around us today. I'm very excited to be part of that. I'm very excited to involve Cornell undergrads as part of the research, Cornell students as part of that research. And I hope maybe if you invite me back in a few years, we'll actually have discovered something out of this. Thanks a lot.
All right, thank you so much, Professor Chung. So we have a few minutes now for any questions. If you have questions on the Zoom, feel free to put them in the chat. Anyone here who has any questions, please raise your hand so that I can run the mic over to you. Any questions? Any at all? Yes.
Thank you for the great talk. Just wondering how you're able to effectively filter out the near field stuff from the far field stuff you're actually looking for. What methods are you using to do that?
Right. So that's a really excellent question, because as you saw, TIME is not designed to line intensity map the galactic center. It's designed to map out galaxies from very far away. And you can see one of the essential things, which is that lines from different redshifts can collide right on top of each other. So the near field stuff will interfere with the far field stuff. One of the ways we try to look past this, look through this rather, is by taking advantage of the fact that there are multiple ways to look at these galaxies. So for example, one of the things I briefly mentioned is that COMAP, for example, is looking right now for emission from redshift 3 and carbon monoxide, but there are other surveys that are looking for signals of large-scale structure at that redshift. Some of those surveys are looking not for CO, but for galaxies in very different wavelengths, which have very different kinds of contaminants. And so by saying, okay, well, how do those two data sets relate to each other, we can actually isolate, this common signal that is really tracing the far field signal, and that is part of what Ella works on, for example.
Any other questions? No? All right, let me check the Zoom to see if there is anything. All right, last call. Awesome. All right. Oh, we have one more. Let me run over to you.
So you said after the Big Bang, the universe experienced cooling, but my question is, if it was a homogeneous structure, like you said, how did it experience cooling? I'm confused. I'm in engineering, so I don't know physics that much.
Right. So if it's homogeneous ever, how did it experience cooling? This comes from the fact that space is expanding. So even though the universe is homogeneous, that does not mean that everything stays the same density of matter everywhere. So as space kind of expands underneath the matter, which is not really an accurate analogy of putting it, but overall what you are seeing is that the density of matter is declining, the opacity of the opacity of matter is roughly related to the density of matter. That means the energy is less trapped as you go further and further forward in time. That means you are you're cooling just by virtue of the fact that the density of energy, density of mass in the universe is decreasing as the universe expands.
Okay, thank you.
Any other questions? Andrew, could you check the chat for me? Awesome. All right. Thank you everyone so much for coming. Can we get one more round of applause for Professor Dongwoo Chung? All right. Thank you guys so much. Just as a little reminder, Fuertes Observatory will be open from 8 p.m. to midnight tonight. And if you'd like to get the schedule for the rest of our lecture series this semester, you can find it on our website. Thank you for coming.